Hi friends, welcome to my channel. Let's have a look at problem 39, combination sum. So in this video, we're going to share again a backtracking solution. So actually we practiced this backtracking technique using problem 40. So you are also welcome to watch that video and compare the subtle difference in the solution formats for these two problems. So in this problem, we are given an array of distinct integers called candidates and a target integer called target. So we are required to return a list of all unique combinations of candidates where the chosen numbers sum to target. So we may return the combinations in any order. So here, one thing that is important is that the same number may be chosen from candidates an unlimited number of times. So in other words, an item in the candidate array can be used multi-times. So here are some further instructions, like the number of combinations is bounded above by 150. So let's also look at the constraints. So the number of elements in candidates is bounded above by 30. And the range of the elements in candidates is in between 1 and 200. All elements of candidates are distinct, and the target is bounded above by 500 and greater than 1 or equal to 1, right? So that's the problem. So here, this problem actually is a standard backtracking if we take similar point of view with problem 40. So here, we want to emphasize again that an item can be used multiple times in this problem. So this actually affects the pattern when we write the backtracking solution. So please see the comment when we do the coding. So the idea of backtracking is actually very simple. It's like a brute force solution. So brute force with quotation mark. The reason is that we begin to build the combination for each number. We consider how many times we can use it, and also we traverse all the numbers. If we build a sum and the sum part is larger than the target, so we just stop, and if it equals the target, we're going to add the corresponding combination to the return, and then we do some recursion calls. So this is the standard route. But here, another point is that, so do we need sorting here? So we may use sort here, but it's not necessary. So again, when we look at the solution code here, it's very good to compare this solution format with the solution format of problem 40. There is actually a subtle difference if you compare the two solution formats. So with that said, let's first do the preparation. Preparation. So I'm going to get the length of A. And also, if we like, we can sort. So we can sort decreasingly, increasingly, or just do not sort. So not necessary. So it might help for early stopping, but this probably is not that critical because of the constraints. So with that said, let's initialize a variable called answer. So this answer is going to be the container which holds our combinations. So this is the first step. The second step is the backtracking step. So here we are going to initialize a path which is a list. Path list is mutable, right? So we are going to use this mutable nature. Then we are going to build numbers using this path. Once the sum of elements in the path equals target, we're going to add this path to the answer. So that's the thing we're going to do. So actually we can think of the backtracking hyperfunction as a worker, right? It builds the combination for us. Once it finds one, it will add to the answer container. So that's what we're going to do. So let's call this function f, just for convenience. So we're going to accept two arguments. One is the index and the other is the total, right? Then what we are going to do is that first we look at the stop conditions. So first, if total equals target, so that it means that we build a valid combination. Then we are going to add the corresponding path to answer. So answer append. So path. So here we are going to pass a copy for this path because we are going to use the state to do the following steps. So this is the one stop condition. So here as a remark, when you do the copy, you can also do this because the path is a list. You can also do this one. This plays a similar role. And another stop condition is if total is larger than target, then we do not do anything. We are going to return. So here we forgot a return. So this is actually important. So this return is actually stop conditions. So with that said, let's consider the generic case. So if the total is not yet target, so we are going to continue the process. So we are going to for I in range idx up to m. What we are going to do is that we try to use the current number once. So we're going to append the AI to the path, and then we are going to do a recursive call. So here the recursive call typically will write I plus 1, and then the target, actually the total is total plus AI. But here we are going to write I. The reason is that we can choose I again, because that we can use atom multiple times. So this is actually an essential part for based on the logic in this problem. So if this is the case, then the backtracking step is the following. So we're going to pop from the path, right? Returns to the previous state, and then do the traversal again. So that's it for this backtracking worker, right? So if we call this function, then this function will automatically prepare the output or update the container answer for us. So with that said, let's do this one. So we're going to call, let's call this step 3, so return. So we're going to call this function. So initially we're starting at index 0, and our sum is 0. And then once we do this function call, so the answer will be updated, and we're going to return the final state of the answer. So that's the whole solution for this problem. So this actually provides a format of solution. So with that said, so because this return will be all the possible combinations, so we can do a special case check first. It passes example 1. So let's do a generic case check. So it passes all the case. So let's comment out this thought and do it again. So let's see. Yeah, so it also passes the generic cases. I guess for this video and this specific format of solution, that's about it. Thank you very much for your watching.